So let's continue with the equation of rotational motion. So when you have F equal to ma for this differentiation mass, so we can apply F equal to ma in that diagram here. So like Newton second law. So I have on the left side it F, and I consider now for now it tangential components. So I have d F tangential components. On the other side, if you project that in tangential axis, so we will have m, in this case differentiation mass, time the at time at vector. Okay, now as you can see, for G is we define G at the center of mass and where the body rotates about, and then let's call about the radius from G to the differentiation mass is R, position vector R, position vector R. That if I am time this R in both sides of that equation, then I continue to have df t dot product with position vector on the other side, dm at original equation time R. And if you recall, at tangential component at a point equal to alpha r. If you recall that equation in the first rigid body kinematics, a tangential component equal to alpha r. If you recall, tangential component of a point equal to position vector times the angular acceleration alpha. So that is on the right side. On the left side, as you can see, the tangential component dft have a right angle with the radius. So if we have the dft times r, so basically that is the radius, in this case the moment arm, perpendicular to the line of action dft. If you recall, the moment arm times the magnitude df is basically a moment, right? So df are basically the moment about point G of df, and we call dmg. On the other side, alpha at, I replace with alpha r, so I will have equal to dm alpha times r and in the equation. So with that one, let me rearrange this equation. So we have dmg equal to alpha times r squared times dm. And now let's take integral of this differentiate equation, integral. And as you can see, integral equal to the sum. So dmg, if I take integral, basically the total moment of all the forces acting on that body, about the center of mass. And why we don't care about the Fn? Fn, as you can see, the line action of Fn parallel to the radius go to G. So if the moment arm is 0, so the left side I have that is the basically sum of all the moment about the center of mass acting on that body. On the other side, alpha, recall it in rigid body kinematics is body properties. Any point on that body will be the same. So it not depends on the radius. Any point the same. We can print out to that equation. So we have it alpha, the same. And then we have it r squared. So it's r squared dm. What is r squared dm? Basically, that is a new concept today that we are introduced. And let's call that one is ig. And from that, we can rewrite the equation, and we can box now. It's very important. mg equal to ig alpha. Box that equation. So you see the analogy here. If the body in translation for the Newton second law, F equal to MAG, center of mass. If it in rotation, F replaced with the moment mg about g, and ig, the center of mass, times the angular acceleration. So ag replaced with alpha, m replaced with ig, and force on the left side replaced with the moment. And what is ig that we are going to discuss next? For now, I just call that either a mass moment of inertia. Mass moment of inertia. So let's talk about that. Mass moment of inertia. Ig, the important concept here. Mass moment of inertia. Ig, mass moment of inertia Ig, and that one here we define. Let's make the definition. Ig, what is that? Equal to, that is the mass moment of inertia and here we specify chi. So what is chi about? This will be about an axis through the mass center. Chi is mass center, center of mass, through the mass center. How we can locate the mass center? Recall the centroid distributed load lesson. So mass moment of inertia about the axis through the mass center chi, that we call it Ig. And how will that be measured? It basically, it will measure the resistance to angular acceleration. Measure of resistance. Key point here, resistance to angular acceleration. So as you can see here, go back. Previous video we say F equal to ma, and m is the mass resistance to linear acceleration. It's the same force. If the mass is higher, acceleration is going down. That's why we call it mass is resistant to linear acceleration. Similar to the equation here, as you can see, with the same moment applied on the body, if the Ig is bigger, alpha will reduce, and that's why it's resistant to the angular acceleration. So as you can see, the analogy in those two, F equal to ma, and let's write down here, we have the analogy, and that very important concept. If we talk about the translation, so we have F equal to mag about the center of mass. And now if we talk about the rotations, then talk about the moment, ma about the center of mass equal to Ig alpha. And what is the unit of Ig? That will depends on the system. So we have Ig in that case, as you can see, the units is slug, that is mass, right? Time v square in foot pound system. And then the units will be a kilogram per meter square in SI unit. So that is the Igs. So now I want to show you why it's resistant to the angular acceleration with the short YouTube video in 1 minute. Demonstration about the why Ig, the mass moment of inertia, resistant to the angular acceleration, as you can see there.
Now gravity is applying the same force to both weights. As we clearly see, the object closer to the center of rotation will accelerate quicker around its axis. Now let's apply this to objects that roll. These are two standard objects that are sold by science companies. We see that the one that has more mass in the center rolls a little bit quicker. I want to add a third object here. The ball has more of its mass towards the center than the cylinder does, so it's going to accelerate even quicker. Here are a few homemade pieces that share the same principle. They weigh the same, only the mass is located at different positions. I think this one shows it the best, so let's try it.